Hello, ladies and gents. This time we are going to talk about a covalent bond. Now, a covalent bond involves a sharing of electron pairs. A covalent bond is a bond that holds atoms together by the fact that they are sharing these electrons. And if you look at the name, co means sharing, as in two co-captains of the football team, two co-chairs of the cookie baking committee for the choir, something like that. Valence electrons is another way of saying outer electrons. So covalent is sharing valent or outer electrons. Now, I want you to understand the difference between an ionic bond and a covalent bond because they're two very different ways of holding atoms together. So here's a ketchup and French fry analogy to hopefully make some sense out of this. Let's say two people go into a restaurant and they both order French fries. If the two people were ionically bonded, both people with their fries get ketchup. And this person gets their ketchup and they don't really want their ketchup. And this person is the ketchup wanter and this person is the ketchup giver. And so the ketchup wanter says, hey, do you want your ketchup? And this person says, yeah, I don't care. I don't want ketchup. And it gives its ketchup away very easily. And these two are bonded by the fact that this person wants ketchup and this person easily gives away their ketchup. That's an ionic bond. One thing is the giver of electrons, one is the wanter or taker of electrons that gives you those opposite charges, and that attraction is that ionic bond. But a covalent bond is very, very different. Covalent bond is all about sharing. Let's say a group of people go into a restaurant and they all want ketchup. They all want it. And nobody is willing to give it up. So they say the answer is we are all going to share. I want ketchup, you want ketchup, everybody wants ketchup. So what are we going to do? We're going to share the ketchup. That's covalent bonding. Everybody can be happy. All the atoms can be happy and content if they share. And so it's a very different way of achieving what they want. And what do atoms want? Well, they want a full octet or a full duet. They want to have a full outer energy level. That's what nature prefers. So covalent bonds occur between typically nonmetals and other nonmetals. Now, nonmetals are in this upper right-hand quadrant of the periodic table, plus hydrogen. Hydrogen is our Mr. Special over in this corner. He might live over here, but he really, in his heart, is a non-metal. And they want to have full outer energy levels, but they're not willing to give up their outer electrons. So how are they going to do this? They're going to do this by sharing their electrons with other atoms. Hence, they get covalent bonding. Now, one of the ways that we can represent covalent bonding is with something called a Lewis dot diagram, named for Gilbert Lewis, the American scientist who discovered the octet rule. And I'm not going to personally, in my class, I'm not going to ask you to draw Lewis dot diagrams. In another chemistry course, you may be asked to draw them, but I want you to recognize them and understand them when you see them, because it really helps explain what's going on. When we use Lewis dot diagrams, the symbol, the element symbol, represents the nucleus and the inner electrons, and we use dots for the outer electrons. So I'm going to use this to help explain how water is bonded. Hydrogen is right here. It's in group 1. It has one outer electron. So I'm going to put hydrogen, and with a little dot. The H symbol is going to represent the nucleus of hydrogen and inner electrons. And it only has one electron, so there we go. There's my hydrogen. Oxygen is right here. It's in group 6A, and as 6A, it has 6 outer electrons. Now, I'm going to happen to use X's for oxygen's electrons just to differentiate from hydrogen. Electrons tend to go all the way around an atom before they buddy up, so there's 6 of them. So 1, 2, 3, 4, 5, and 6. So that's oxygen, that's hydrogen. Now, when nature puts a water molecule together, how does it mix and match them together to make H2O? Well, if I've got an oxygen that looks like this, nature uses the hydrogen to fill in the holes. So a hydrogen goes here, and a hydrogen goes here, and this thus creates a water molecule. 2 hydrogens and 1 oxygen, and this right here is a covalent, co-sharing, valent outer electrons, 2 covalent bonds that holds water together. It also gives us a little bit of information about the structure of the water molecule, and molecule structure becomes very important when we start talking about covalently bonded compounds. Let's look at another one. Let's look at hydrogen chloride. Again, hydrogen, 1 outer electron, and chlorine. Chlorine is a halogen, group 7. Chlorine has 7, so 1, 2, 3, 4. They go all the way around once, and then they buddy up. 5, 6, 7. The goal for chlorine is 8, a full octet, so it has 1 hole here. Hydrogen is a wee little atom. It will be happy and full when it has achieved a duet, so hydrogen has a little hole here. Nature puts these two together so they both have full outer energy levels, so it looks like this. Hydrogen and then chlorine, and they just cuddle up like this. And you end up with this structure, and that makes hydrogen chloride. Simple as that. And this right here is my covalent sharing electron bond. Now, drawing all the dots, as you see, gives us kind of an explanation of what's going on, but drawing the dots can be messy and confusing. So these dots are often replaced with a single line. So you'll very often see water molecules not written like this, but written like this, where each line represents a shared pair of electrons. Hydrogen chloride is very often written like this, and when you see this written somewhere on the internet, in a book, whatever, it is showing you not only the formula, the chemical formula, it is showing you something about the structure of the molecule, how it is put together, how the molecule might look if you could actually see something that incredibly small. And the shape of molecules have a lot to do with how they act, how they chemically bond. Now, what I was just showing you, these back here, these are single bonds, single pairs of electrons that are shared. But the cool thing about covalent bonds is you can also share 2 pairs, and those are called double bonds. And when that happens, then it's represented by 2 lines. A classic example is carbon dioxide. Carbon is in group 4A, so it has 4 outer electrons. And in carbon dioxide, kind of wacky how it bonds. It looks like this. Oxygen has 6 outer electrons, and it goes like this. The oxygen's outer electrons are going to go like this, and like this. And then this shared foursome, carbon now has 8, 1, 2, 3, 4, 5, 6, 7, 8. Oxygen has 8, 1, 2, 3, 4, 5, 6, 7, 8. And so does this oxygen. Every atom has a full octet, and this is more simply written like this, where the double bond is represented by 2 lines. Now, carbon dioxide is what you exhale from respiration. Now, carbon monoxide with 1 oxygen occurs when there's combustion combustion and not enough oxygen present. Very different situation. Then you get the carbon atoms and the oxygen atoms like this, sharing actually 6. And it's going to look something like, make sure I get these the right spot. I think I got those messed up. Something like that. Oxygen's going to have 1, 2, 3, 4, 5, 6, 7, 8, and carbon's going to have 1, 2, 3, 4, 5, 6, 7, 8. more simply written as 1, 2, 3 lines, and that is a triple bond. So you can see the dots get confusing real quickly, and we use the lines much more often. The bonds get stronger as you get more electrons being shared. So as you can imagine, a triple bond is going to be much stronger than a double, than a single. And that is going to have a lot of effect on the chemistry involved when you burn something or something breaks or cannot break. And we'll talk more about that later. All right, see you later. Bye-bye.